time. So the next presentation is from, let me hope I said it right, Nobuhuri Miki, and it's about SRv6 tunnel implementations in user-space datapath.
Hello, I'm Nobuhiro Miki from SRv6 Corporation. The title of my talk is SRv6 tunnel implementation in user space datapath. Let me start my talk with background. Our private cloud at SRv6 Corporation is designed to realize VPC by employing SRv6 L3 VPN provided by BGP. For instance, as shown in this example, when we have two tenants highlighted in red and green, our cloud provides an independent virtual network for each of these tenants. Additionally, we have large-scale OpenStack clusters with OVS, so we are considering the integration of SRv6 L3 VPN with OVS, and we want to provide flexible and high-performance SRv6 data plane for VMs. You may already know this, but let me introduce SRv6 packet format once again. The SRv6 data plane inserts tunnel information into the segment routing header, which is one of the IPv6 extension headers. The segment routing header has a field called a segment list, where a list of transit nodes can be listed. We have designed and implemented data plane in OVS to meet this specification. This feature is already released in OVS version 3.2. Here is a brief overview of what we did. In OVS, the tunnel is abstracted as a virtual port, and we followed this practice for the SRv6 tunnel as well. Currently, the data plane is implemented only in user space. We haven't touched the kernel data path yet, but it is under consideration as a future work. We support both IPv4 and IPv6 as inner packets. Unlike other tunneling protocols, SRv6 allows user to specify a list of transit nodes as a segment list. So a new dedicated option for this purpose has been added. Okay, so how can we use it? The setup process is similar to other tunneling protocols such as VXLAN and GUE. What's needed is to set the type to SRv6 in the port settings. Here, local IP and remote IP are common settings for all tunneling protocols, and these mean both ends of the tunnel. Additionally, the new dedicated option is used to specify segment list. In this example, the SRv6 packets reaches router 4 via router 2 and router 3 by following the segment routing path configured in router 1. If it is omitted, it is automatically treated as a segment list of length 1 containing the remote IP address only. Performance is one of our most interesting parts. We used Linux Connect X6 25G NIC and ran the micro benchmark. This implementation targets user space, so we needed to set up OVS with DPDK. The performance differs between single and multi-flow, so I will explain in detail in the following slides. First, the case of multi-flow. In this case, RSS worked as expected, and theoretical maximum performance was achieved for all packet sizes. On the other hand, the case of single flow showed different performance. Let's start with the encap case. In this scenario, as shown in this figure, both inner and outer headers have the same IP addresses for all packets. So RSS doesn't work, but this is the expected behavior. In other words, this figure shows performance per core. Next is the decap case. Now, this is interesting. In this case, decap action was performed on packets with multi-flow inner header. Please note that as shown in this example, the inner headers have different addresses, while outer headers shares the same addresses. In this scenario, inner header-based RSS was expected, but it seemed not to work. As one approach to this issue, we added a new option to calculate flow level in outer header. This option is similar to a parameter implemented in the Linux. We can choose from 3 values listed in the table. If compute is selected, it sets flow level to a hash over the layer 3 and layer 4 fields of the inner header. We think this is useful not only for RSS in hypervisor case, but also for load balancing case such as ECMP in the whole underlay network. Even though we could calculate the flow level, we have not yet achieved flow level based RSS on the SRv6 decap side. Since Linux probably supports it, we want to solve this issue. And we are, of course, interested in the kernel datapath. Here are some reference materials. We would like to take this opportunity to express our thanks to the OBS community for their many reviews and helps. We hope to keep contributing to the OBS community. I'd be happy to receive any comments. That's all for my presentation. Thanks all for listening.
All right, thanks a lot for your presentation. It was really nice to see. Also, thanks for your all your upstream work and your. I think you were on the Hall of Fame, so that's very nice achievement. So thank you for that as well. And then I think you can come online if you want to. Hi, welcome. I'm trying to see if there's any questions at the moment. Let's see. I see no questions here. No questions in the chat yet. All right, so that's good. So I might have a question, and that is on your slide of things to do. You listed quite some items to do next. Do you have any preference on stuff you want to work on first, or are you just slowly looking at the kernel, or are you more interested in the user space at the moment?
Now we're interested in for performance tuning, especially we want to focus on RSS, and of course in the future I want to implement kernel datapath for SRv6 tunneling.
Okay. Yeah, I see someone is asking a question, and he says, I'm interested to see if for layer 2 VPNs, and probably with the kernel datapath. So do you have any feedback on that?
Yeah, of course. I'm also interested in L2 VPN, of course. And yeah, I'm, of course, and I'm also interested in kernel datapath. So I want to work with Thomas and yeah, work together. Yeah.
All right. So that's good. So we will see some more patches from you coming soon. So thanks for joining the community and making your work available to everybody. I really appreciate it. So yeah, thanks very much for your talk, and hopefully maybe next year we have a follow-on talk.